Ising model. Today we are going to take it a bit slow because I was sick yesterday while preparing the lecture. Now it's a bit better, but okay. So what's the Ising model modeling? So the idea is we want to have a probabilistic modeling of the behavior of a ferromagnet. Okay. Ferromagnetic metal. Okay, so let me first tell you what's the behavior of a ferromagnetic metal. So what is the way that you're going to create a magnet? So usually what you do is you take a piece of metal, okay, and you place it in a magnetic field. So let's say, okay, and what will happen is that if you place the metal, at the vicinity of an intense magnetic field, and then you take it away, then it will remain magnetized. And in fact, whether or not it remains magnetized depends on the temperature at which you're doing the experiment. So if the temperature is low, then after you take your metal away, it remains magnetized. So I'm just drawing the but if T is smaller than the critical temperature, okay, then it's not magnetized. Okay, and this temperature is called the Curie temperature. And furthermore, what happens is that if you have some magnet and and you heat it above the Curie temperature, it will lose its magnetization. Okay, maybe I would put this away. Okay, so what's our starting point to model this? Well, the idea is we want to model our metal by a lattice, and to say that, it's made of, let's call these things atoms. So it's a lattice of atoms, and each atoms behave like a small magnet, so it will have an orientation. Okay, and what will happen is that the size of our lattice will be large. So for this reason, we are going to study things in the limit when n goes to infinity. Okay, what we are going to look at is really a probability on the set of configuration for those dipoles and for the orientation of those dipoles. And what we have is that, well, first, dipoles want to align with each other. And second thing is that they want to align with well, the external field if there is some. Okay, so what we are going to do is, in fact, further simplify the picture. So instead of looking at, well, saying that our dipoles can have any orientation, we are going to make the orientation of the dipole completely one-dimensional. So they can be pointing up or pointing down. And this will simplify the analysis. So one-dimensional. So up. So I will call the dipole orientation spin. Okay, so I have two possible values for the spin, up or down, and in most cases we will just say +1 or -1. And a second thing that we are going to consider is we are going to make the interaction nearest neighbor. Okay, so normally, if you have a magnetic dipole somewhere, well, it interacts with the whole space and in a way that decays like a power of the distance. But, okay, in our case, we are just going to say that this influence between spins, it will just be nearest neighbor in the sense that, yes, this guy will want to be aligned with its neighbor. This will be the only thing we will require. Okay. And okay, this is basically it. So now, once I've said that, I've basically almost defined the Ising model. What I have to introduce now are kind of the basic way to define okay, a model in statistical mechanics. So generally, what do you do? So first thing we are going to do is to define a state space. So omega. And this is the set of all possible configurations of our system. So, okay, I will then tell you what's the state space in the specific case of the Ising model. Then we take H, which is an energy functional, which goes from omega to R, which to each configuration of the system associates an energy. And then from this, we define for a fixed parameter beta positive, we define the Gibbs distribution of the system, which is a probability measure on omega, which to each configuration gives a weight which is proportional to exponential minus beta h of omega. Okay, where this thing is just the sum over all configuration of exponential minus beta h of omega. Okay, and for yes. Okay, so I mean, what this means is that under the Gibbs distribution, so and beta is what is called the inverse temperature. Okay, so basically what we have is that the system wants to sit in the configurations with lowest energies. Okay, but nonetheless, I mean, all the configurations, they have positive probability. And under the Gibbs distribution, somehow there is a kind of a balance, well, kind of a competition between energy and entropy, in the sense that, okay, configuration with lower energy are the most probable, but maybe they are not less as numerous as configurations that have a bit higher energy. So this is the very general framework in which statistical mechanics work. And now let me tell you, in the specific case of the Ising model, okay, what omega is, and I will twist a bit the definition to make well, the writing easier during this part of the class. So, okay. So what is our state space? So we start with lambda, which is a subset of ZD. Okay, and we are going to consider ZD as a lattice as before. Okay, so in particular, we'll say that X is a neighbor to Y if the one norm of X minus Y is equal to 1. So we start with a finite subset of ZD, and we define omega lambda, which is just minus 1, 1 to the lambda. So it's the set of spin configurations in a finite subset of ZD. Okay, then I have to define my Hamiltonian. So I don't know, I will change the definition immediately. So for the moment, I will just write it with a bar. Okay, so the reason is that what I'm going to give you now is really the definition that makes sense physically. And then basically it will be easier for me to write things without minuses and stuff like that. So I will just change the definition immediately. Okay, so an element of omega, I will call it sigma. and it will be just be the value of sigma at x. It will be, I will use the notation sigma index x. And I define an energy functional on omega lambda, which is just, well, there are two parts. So first thing is I want to account for the fact that neighboring spins wants to be aligned. So I'm going to say that if neighboring spin here I'm summing over the pair of neighbors in my box. Okay, so let me just write the Hamiltonian and I will comment afterwards. Okay, so in my energy, I have two terms. So the first term is for, well, the interaction between spin. So what I'm going to say is that my energy is higher if two neighboring spins are differing. Okay, so if on an edge, basically, I have a plus spin and a minus spin that are neighboring, basically, it will make my energy well, the energy contribution for this edge +1, while if these have the same values, the energy contribution for that edge will be -1. Okay, just because of this minus sign here. Okay, and this second term is accounts for interaction with the external field. So I'm supposing that my box is submitted to a field which is well, pointing either up or down depending on the sign of h, and well, whose intensity is given by the absolute value of h. Okay, and yeah, what I'm saying is that well, the sigmas, they want to be aligned with h. Okay, so basically, if h is positive, the sigmas wants to be positive. So having positive sigma makes your energy lower. Okay, so this makes sense. And the intensity of how much you want to be aligned, it really depends on the absolute value of h. Okay, so okay, so what I'm really interested in is really minus beta h bar of sigma. Okay, so this is equal to beta times the sum over x, y, lambda, x neighboring y, sigma x, sigma y, plus beta h bar sum over sigma x, x. So, okay, basically for this reason, I will just call this thing h. Okay, this thing also depends on lambda, so we might want to keep this dependent here. And this is what I will call h lambda beta h. Okay, so this is kind of minus the Hamiltonian, and I've taken the temperature inside. And also for the magnetic field, okay, I will just call h this term. Okay, and what you have to remember is that here, okay, h can be real, beta is positive in general. Okay, and now we define mu lambda beta h, which is the probability which to sigma gives a weight which is proportional to exponential h lambda beta h sigma. Okay, so I mean, just for commodity, just not to have to have lots of minors that cancel each other. Like I define my h without the minus, and okay, then there is no minus here. Okay, so is it clear what the definition of the Ising model is? So take a box of ZD, okay? We might do a small digression about the case d equal 1, but really you should think about d larger than 2 for things to be interesting. And yeah, you consider a measure on set of spin configuration, which depends on two parameters, beta, that I will call inverse temperature, and h, which I will call external magnetic field. And yeah, the weight of each configuration is given by the following. Okay, so as for percolation, what we are going to be interested in is really phase transition for the system. And what is phase transition? You know, it's when the behavior of the system changes abruptly when the parameters pass a certain threshold. Okay, so to observe the phase transition, somehow we will have to send the size of the box to infinity. Okay, if you look at okay, so I mean, if you fix the size of the system, and if you fix the configuration and look at how its probability varies with beta and h, well, it's a bit boring. You know, you have a function which is very regular in beta and h, so the behavior of your system will vary, I mean, continuously in beta and h, and even more than continuously, because this function here is infinitely differentiable. Okay, so in order to see something interesting, what we are going to do is to send the size of the systems to infinity and see what happened. So maybe okay. Maybe before thinking about the size of the system to infinity, there is something else I have to talk about, which is the notion of a boundary condition. So this is something that will come into the game when we consider larger and larger boxes. What we are going to do is to define the Gibbs measure in a box, but while the spins outside of the box have already been determined. So it has to be another color here. I don't know if the blue looks right. So, okay, so I'm going to consider, okay, so a larger state of configuration, which is the configurations on all ZD, okay, and given this is minus 1, 1 to the ZD. Okay, so the set of spin configuration on the whole lattice. And given such a spin configuration, what I'm going to define now is a new energy functional, which is basically just the one we had before, but where we are adding interaction with neighbors. So okay, where these are the set of external edges. Okay, and here implicitly x is the one in lambda and y is not the one which is not in lambda. Okay, so I am just taking the same thing as before, but I'm adding an extra term which accounts for the interaction of the spins with the boundary, okay, with the external boundary. Okay, so I mean, even though I define eta on everything, okay, including lambda, in fact, the only values that matter in order to define my Hamiltonian will be these values on the boundary. Okay, and well, eta takes value plus or minus 1, but somehow if it could take the value 0, this original Hamiltonian would correspond to the case where eta is uniformly equal to 0, so I will just use a notation mu0, z0, and h0 for that. Okay, so now let me tell you what's our kind of ultimate goal here. Okay, so we want to consider a sequence of boxes that grows to be the whole ZD. So what we want is that lambda n is finite, lambda n plus 1 includes lambda n, and 3, that the union over all lambda n is equal to z. And now what we would like to do is, well, to be able to take the limit of this measure when n goes to infinity once we have fixed the sequence going to ZD. Okay, because we are interested in very large values of n. These are very, very, very large boxes. This is what gives you this is what is relevant for the model. So yeah, mathematically, the limit when n goes to infinity is really the thing to look for, the large box limit. The problem we have is that, well, this is a probability measure defined on omega lambda, so somehow the state space is different for every n. Okay, so it's not really the right context to take the limit. So let me tell you in which sense you can try to look for a limit. So, okay, I mean, just here I'm saying that mu, okay, this is a small, here I'm saying that mu is a probability measure, and of course, when I say mu of sigma, what I really mean, okay, is mu of the weight of the configuration, so the probability of the weight of the set which is made of only one configuration. Okay, so I just hope that this. Okay, so what I'm going to do is to fix A included in ZD, which is finite, and look at this. So I'm going to look at the distribution of the spins that are in A. Okay, so this is always well defined when n is large enough. You know, if the union is equal to ZD after a certain rank, okay, if I fixed A will be included in lambda n. Okay, so this is. Okay, so I can ask myself whether this thing converge. Okay, and in fact, I can ask myself whether this thing converges for every A. Okay, and if this converges for every A, somehow, well, there has to be a coherence between the limit for a given set A and the limit for a given set B. So for instance, if you take A included in B, then if you take the limit for B and you take the projection on -1, 1 to the A, then this projection has to be the limit for A. Okay, so if you have this set of coherent projections, basically, so having a limit for every A is sufficient to define a limiting probability on minus 1, 1 to the ZD. Okay, because if you have the limits, they give you a set of coherent set of marginals, and if you yeah, okay, I've not even taught that in my measure theory class, but the idea that there is a general result called Kolmogorov extension theorem that says if you have a set of marginal probabilities that are coherent between themselves, you can basically define the probability on the larger space for which the projections are the one that you, okay, for which the finite dimensional projections corresponds to your this probability you started with. Okay, so. So if you're given this limit for every A, okay? Or another way to say this is basically taking this limit, like it tells you basically that you can define the probability of all cylinder events in a coherent manner. Okay, and what Kolmogorov extension theorem tells you is that if you have a measure which is well defined on the set, if you have something which is yes, well defined on the set of cylinders, you can extend it in a unique fashion to the full sigma algebra. Okay, but okay, these are just technicalities, but the idea is, okay, in a sense, this allows you to define a limit, and you would want to know what are the properties of this limit. Okay, so more precisely, the main question we would like to answer is, do we have a limit? is it the same for every sequence lambda n? Okay, well, these two questions maybe they are a bit of the same. So. Does the limit, so it's kind of clear that the limit will depend on beta and h, okay, but what is less clear is whether the limit depends on eta, okay, because well, the boundary, it kind of moves away from A when A goes, when n goes to infinity. Okay, so my writing is bad. No? Any, yes? Oh, it's just the angle, okay. So, yeah, so does the limit depend on what we have chosen as a boundary condition? Okay, if you remember, eta was a the kind of extra boundary term that we had in our Hamiltonian. And see what can we say about magnetization. So okay, so for instance, we would like to know if in the limit, spins are more likely to point up or down. Okay, so if you remember the original experiment, we would like to know whether in some cases, in the absence of magnetic field, we could have still a remanent magnetization. Okay, which would be due, say, to the presence of a boundary condition that would correspond to like a past exposition to a magnetic field. Magnetization, yes. So, okay, so I guess at this point everything is a bit vague, and now what we are going to do is try to basically build up a theory that allows to answer all of these questions. Okay, and so let me write the answer here, which is so what happens very often in statistical mechanics is that you can get a lot of information about the system just looking at the partition function. So I don't know if I've said it, but okay, so this renormalizing factor Z Okay, just the thing that I had to put in the denominator so that I could make sure that mu is a probability. It actually happened that this thing, which is just a number, can help you to understand the behavior of the system. And more precisely, what you have to look at is how this thing varies when beta and h vary. Okay, so this is what's called the partition function. Yes? H is a magnetic field. Okay, I mean, here really H is the inverse temperature times the magnetic field. But because I will consider these two, I mean, very often we will fix one parameter and vary the other. So, yes, basically, H gives you the direction in which spin wants to align. Okay, so if H is positive, spins wants to be plus. Okay, if H is negative, they are more likely to be minus. And how much they want to be plus depends really on the absolute value of H. Okay, and you see that in the Hamiltonian. Basically, I should have. Okay, so basically, I mean, this appears in the exponential, so the higher it is, the more probable the configuration sigma is. And basically, here, each sigma that aligns with H will give a positive contribution to this big H. Are there some other questions? Okay, so in fact, what we are going to study is not directly Z, but it's log. This is where the info. This is the more meaningful quantity. And we are going to define okay, so the free energy it's just the log of the partition function divided by the volume of the box you're considering. Okay, I'm just using this. This is just the same thing as this. Okay, it's just a number of vertices that I have in my box. And okay, I mean, there is a physical explanation about this term, free energy. I will not go into that. Also, what I'm defining is not really the free energy. You can see in the lecture notes by Friedli and Velenik that they call this pressure. And actually, they are right. Like, if you look at the unit, I mean, okay. Here we are in mass, so we don't really care about the physical dimensions, but like, well, this is a log, so this means that basically this is a dimensionless thing, and somehow you would have normally to divide by beta in order to get something which is homogeneous to an energy. Okay, so I mean, beta is the inverse temperature, but it's in fact the, okay. Basically, H is an energy, so this means that beta, whatever it is, okay, it has to be homogeneous to the inverse of an energy. So if you want to have something which looks like an energy, you have to put 1 over beta here. Okay, so the right way to call this would be pressure. Most people call it free energy. Do whatever you want. Okay, so one first observation I will make about it, which we will use later, is that it is a convex function of beta and h. While proving this, you will see that this gives you also that you will. Okay, the proof I will give you will kind of back my claim that some important information about the system are encoded in the free energy, and thus in the partition function. Okay, so lemma. The free energy is convex in beta and h. Okay, so what I'm going to do, in fact, is not prove exactly this. I'm going to prove that if you fix h, it's convex in beta, and if you fix beta, it's convex in h, okay, which is strictly weaker. But I think what you get out of this proof is informative. If you really want to prove convexity jointly in beta and h, what you can do is use Hölder inequality. Okay, and this is also instructive, and the correction of this exercise is in the book. So. Okay, so what I'm going to do instead is compute the second derivative in h and in beta, and I will not compute the cross derivative, which would be necessary to get the full convexity, but I could do it as well, in order to show that they are positive or non-negative. Okay, so let's start with the derivative with respect to h. The one with respect to beta is exactly identical, so what I will do is put all the details of this computation, so please ask all the questions you want. And for beta, I will just write the conclusion, which is very similar. Okay, so I'm taking the derivative of a log. Okay, so let's just forget about eta and lambda. This might make the computation more readable. Okay, so this is what I get. Now if I take the derivative of this is a sum, right? So this is the sum over sigma in omega lambda of exponential h beta h lambda beta h, well, okay, eta of sigma over z beta h. Okay, so you have a sum of terms, so I just take the derivative of each individual term. And now if I take the derivative with respect to h, you see that what's going to fall down is this. Okay, so what we get is the sum over sigma in omega lambda, the sum over x in lambda sigma x, and then I get exponential lambda beta h, and then I get my partition function there. Okay, so now we can recognize something here. Okay, I mean, basically, what we are doing is, okay, this is exactly the probability of the configuration sigma. Okay, so we are summing over sigma, well, the probability of the configuration sigma times the function of sigma. So what we are just doing is taking an expectation with respect to mu. Okay, and these brackets, they will be the notation which is used for expectation with respect to mu. Okay, and this thing well, this corresponds to the total magnetization in my box lambda. Okay, it's just the sum of the spins that I have in lambda, so it gives me the total magnetization. Okay, so if you take basically the derivative of your partition function, basically you get the expected total magnetization divided by the volume. Okay, so like the average magnetization per unit of volume after taking the average with respect to the Gibbs distribution. Okay, we are interested in convexity. So we have to consider second derivative. Any question on this computation? So if you take again derivative with respect to h, so what you get is that this is equal to this. So Okay, this is the quotient. So what I can do is, well, apply the general rule that I have for derivative of the quotient. So I have the derivative with respect to h of sum over sigma in omega lambda m lambda of sigma exponential lambda beta h over z beta h, and then I obtain minus d h z beta h over z beta h square times this. Okay, now when I'm taking the derivative here, okay, when this does not depend on h, so I just have to take the derivative of the exponential, and what happens is exactly the same thing as before, that there is this term m lambda of sigma that goes down from the exponential. So what I get is the sum over sigma in lambda omega of m lambda sigma square times exponential h lambda beta h eta sigma over z beta h. And here I've already done the computation. So I know that this derivative of z beta h over z beta h I only have one of them because one of them is used here. Okay. So when I have this, I know that what I get is exactly this. So this is m lambda eta lambda beta h to the square. Okay, so what I get is this. In the end, okay, because this is an average with respect to mu. And therefore, this is just a variance. So this is the variance with respect to mu of m lambda. And I've dropped all the indices in the end. Okay, so this gives you convexity in H. In beta, in beta you get kind of the same thing, except that what goes down when you take the derivative with respect to beta is exactly this. Okay, so what you get in the same manner is that the derivative with respect to beta of log this is equal to the expected value of the sum over xy in lambda x y of sigma x sigma y plus the sum of x y in delta lambda of sigma x eta y eta lambda beta h. Okay, and if you call it n of sigma, okay, so basically the first derivative gives you the expectation of n of sigma, the second derivative will give you the variance of n of sigma. Exactly in the same, for the same reason. It's exactly the same computation. Okay, so for these reasons, these things are positive. Okay. So now let me tell you about a few basic properties of this, which are simply due to symmetry. So okay, so what can we say? Well, basically, you can just, well, this thing is almost symmetric in H, well, in the sense that if you replace H by its opposite, well, what you just have to do to recover the free energy with H is reverse the boundary condition. Okay, so in particular, what we have is that f lambda 0 beta h is equal to f lambda 0 beta minus h. Yeah, and I think this is pretty, I remember, okay, there were supposed to be 3 properties, but, okay, so these are basically 2 in 1. What's the other kind of symmetry that there can be? Ah, yes, okay, so. Just check. Okay, I will check next time, but basically, okay, let us stick to this, which is basically the most important one. Okay, so why is this true? So if you look at the application which to sigma associate minus sigma, okay, well, it is a bijection. It is a bijection. Okay, minus sigma is just a configuration for which at x you attribute the value minus sigma x. Okay, so this is a bijection, so therefore what you have is that the sum over sigma in omega lambda of exponential h lambda beta h sigma this is equal to the sum over sigma in lambda omega of exponential h lambda beta h minus sigma. Okay. Now what you have also is that h eta lambda beta h minus sigma, it is equal to, okay, so if you change sigma by minus sigma, you're not changing anything here, okay? You're not changing, here you're changing this by a minus. Okay, so you'll be adding a minus here. So you're basically changing h by minus h. And okay, if in this you're considering the boundary term, okay. If you replace sigma x by minus sigma x, you will have to replace eta x by minus eta x in order to get the same thing. So this is equal to this. Okay? So therefore, this is equal to this. H lambda beta minus eta h sigma. Okay, and therefore you get that this is equal to z lambda beta minus h minus eta. Okay, and you get this this symmetry in the free boundary case, and this kind of symmetry provided that you also symmetrize the boundary condition when you have some boundary condition. Okay, so since we want to take the limit of, we want to consider the limit of our system when the size of the box tends to infinity, maybe the first thing we can try to do is to take the limit of this function when the size of the box tends to infinity, okay? And try to get some information out of this. Okay, so here. So this is a theorem. I think I'm going to prove a few things about it, but the main proof will be for next time. So. No, okay, and I need to introduce some notion before introducing the theorem. Okay, so so far when I wanted to take I wanted to enlarge my box and to take the limit to get the whole lattice. The only requirement I would have was, well, lambda n finite, lambda n increasing, and lambda n eventually covering the whole space. Okay, and this is actually sufficient if you want to get the limit for the measure. But to get something relevant when you take the limit for the free energy, basically you want to take another assumption, which is that the size of the boundary of lambda n is negligible with respect to the size of lambda n. Okay, where here it's not really important how I define the boundary, but let's say that here this is the external boundary. So this is the set of x's in ZD, x in lambda c, such that there exists y in lambda, x neighboring y. Okay, and if these four things happen, so this is the definition, so if 1, 2, 3, and 4 hold, we say that lambda n converges to ZD in the Van Hoff sense. And our theorem is that if lambda n converges to ZD in the Van Hoff sense, then the limit when n goes to infinity over f lambda n eta beta h exists and does not depend on eta nor on the sequence. Lambda. Okay, so maybe when you give definitions, it's good to give examples. So take lambda n being equal to minus n to the d. This converges in the Van Hoff sense, so this is something you can check. Well, this is basically the isoperimetric inequality on ZD. And maybe an exercise would be to find a sequence lambda n such that 1, 2, 3 hold, and 4 does not. Okay, so what we are going to do now to conclude is some preparatory work for the proof of this theorem. What I'm going to do basically is to prove this part first. Okay, that the limit, if it exists, does not depend on the boundary condition. The reason why I want to do that first is that this kind of illustrates where this assumption is used and why you have no chance for this theorem to be true if you don't have this. Any questions about the definition or the theorem? Okay, and maybe one more comment about what we are doing. You just saw that this finite volume free energy was related to the magnetization of the system. So basically, we hope that this is conserved in the limit, and knowing something about this infinite volume free energy will give us some information about this infinite volume model that I talked about, okay, that you obtain by taking limit of finite dimensional marginals. Okay, so okay, so to prove that the limit does not depend on eta, it's sufficient to prove that this thing is equal to 0. Okay, so really, it's not complicated to prove that the limit cannot depend on eta even before proving the existence of the limit. Okay, and here maybe it will be easier if I just take 0 here and there is no loss of generality, okay, because then I can just apply triangular inequality to get this. Okay, so so what's the idea here? Well, maybe what I just have to try to control is the difference between the two Hamiltonians, okay, the two H's. And because then what I'm basically doing is just taking a sum over the exponential of them and then taking the log. So if I have a good control on the difference, then this should be conserved as far as this operation. Okay, so lambda beta h sigma this thing, it's equal to the sum over x lambda y lambda c x neighboring y sigma x, okay, beta here, sigma y, eta y. Okay. So what I have is that this is equal to this, and this is smaller than beta times, well, basically the number of edges between lambda n and its complement. Okay, so this set of edges, this is what I called delta lambda n. And you have to take the cardinality here. Okay. So now how can I conclude? Maybe I have to do the... Okay, maybe I have to do the two inequalities separately. And because they are exactly the same, we can do only one. This will be sufficient. So what we have is that z lambda beta h eta, this is smaller, this is equal to the sum over sigma omega lambda exponential of this, which is smaller than sum over sigma omega lambda exponential lambda beta h0 sigma times exponential beta delta n, delta lambda n. Okay, the number of edges in linking lambda n to the boundary. Okay, so this is smaller, well, this is equal, sorry, to z lambda beta h0 exponential beta delta lambda n. Okay, so now if you take the log and you divide by lambda n, what you get is that f lambda beta h eta is smaller than f lambda 0 beta h plus beta times delta lambda n over lambda n. Okay, this 1 over lambda n is in the definition. Okay, well, I mean, when I'm doing this, I'm just taking the log, so I'm conserving the inequality. So this log transforms this multiplication into an addition, and then I'm dividing by the volume. And now this thing is exactly something that tends to 0, because, I mean, ZD has a bounded degree, okay, the uniform degree equal to 2D, so the size of the boundary, okay, it's comparable to what we have is that this, okay, I'm not being, yeah, I think this might be the best we can do, actually. So this has to be true. Okay, because basically for each site in the external boundary, I have of at most 2D outgoing edges. Okay, and well, I have 2D outgoing edges. Some of them might be in this, some of them might not. So I have this inequality. Okay, so this thing is smaller than beta times 2t times this. And this goes to 0. And exactly the same thing, okay, but well, okay. What you can do is say that this is larger than this. So you get minus, okay, 2 beta. Okay, and here, okay, of course, we are a bit rough in the way we are taking inequalities, but what we are missing here is I mean, the level of imprecision is just a matter of a multiplicative constant. So if the boundary is really big, like this term will be important. Okay, I mean, the terms that we have bounded by this will also be important, so there is not so many chance of having this being true if you don't have convergence in the Van Hoff sense. So this is the reason why this condition that the boundary should be relatively small is important. Okay, and this is something I won't say anything about, but well, a consequence of this is that if you try to study the Ising model on a regular tree, for instance, it has a really different behavior simply because on a regular tree, I mean, there is no Van Hoff convergence. Okay, so the boundary still has a huge influence because the size of the boundary of any box is always comparable to the size of the box. Okay, so let me just say a last word about the proof of this theorem before we conclude. So we are going to come back basically to the first lectures of this course. The key word here is superadditivity. Okay, so and here we have to be a bit careful. So okay, so I want something to be. If I want something to be super additive, basically, this means that I want the z to be super multiplicative. Okay, and maybe we have to do something in order to make sure it's true. So okay, so. So because of what we have just said, what we have just proved, we can only consider the free boundary case. This is the first simplification. Okay, if we have convergence in the free boundary case, what we have just proved says that we have convergence for every boundary condition. So the Hamiltonian we will consider will be exactly this. Okay, and here there is no term with eta which is hidden. It's really okay. So now if I want my thing to be super additive or subadditive, I want to make sure that when I'm considering, so what I want, okay, basically, is to define a variant of z which is such that z lambda 1 union lambda 2 is smaller. Oh, okay, it's larger. Maybe it's larger. Okay. let me say larger, it would be easier. Than z lambda 1 times z lambda 2. Okay, so I don't know if you remember what we did for the self-avoiding walk. We were saying that you should take the number of self-avoiding walk of length n plus m. It was smaller. Okay. So let me make it like this, just for the sake of having something similar. So we say that the number of self-avoiding walk of length n plus m, it was smaller than the number of self-avoiding walk of length n times the number of self-avoiding walks of length m. And out of this, we had that Cn to the 1 over n converged. Okay, so meaning that log Cn over n converged. Okay, so here we want to have something similar, except that basically you replace addition by disjoint union, okay, and that's it, okay, and here, I mean, when what you divide is going not to be n, it's going to be the cardinality of the box. Okay, so it's not completely true that this is sufficient. Okay. This does not imply in general that 1 over lambda log z lambda converge when this goes to ZD in the sense of Van Hove. But it helps a lot, okay, and you need only a few more ingredients to conclude. So the big trouble we have here is that this is actually not true for our partition function, so we have to modify it a little bit. And for this to be true, basically, what we would like to be true is something like this. So, we would like h lambda 1 of sigma 1. Okay, sigma 1, sigma 2 is smaller than h lambda 1, sigma 1, sigma 2. Okay, sigma 1 belongs to omega lambda 1, sigma 2 belongs to omega lambda 2. So sigma 1, sigma 2 is just an element of omega lambda 1 union lambda 2. Okay, so if you have this, then you just take the exponential, you take the sum, you get this. Okay, just because the sum over sigma 1 in omega lambda 1 sigma 2 times the sum in sigma 2 omega lambda 2. Okay, it's the same thing as the sum over sigma in omega lambda 1 union lambda 2. Okay, there is a bijection between this Cartesian product and this. Okay, so let me just write the modification which is necessary to make an H for this to be true, and wrap the whole thing up, and then we will continue next time. So okay, so what's the difference between this and that? Okay, so you have lambda 1, which is here, lambda 2, which is here. Okay, So if you take the sum of the sigma x's, these things, I mean, the sum of the sigma x's in lambda 1 plus the sum of the sigma x's in lambda 2, well, times h. Well, if you sum them, you get just the sum of the sigma x's over lambda 1 union lambda 2. So here it's exactly additive, so you don't need to modify anything. When you take this thing, basically on the left-hand side, I would be summing over edges in lambda 1 and edges in lambda 2. And here I'm summing over edges in lambda 1 union lambda 2, meaning that in particular, if lambda 1 and lambda 2 touch each other, I have these edges that are counted there and not there. Okay, so in order to have something like this, what I want to make sure of is that these edges have a positive contribution. Okay, and for my definition of H is simply not true. Okay, I have to sum over all configuration, and there are some configuration for which they would have a negative contribution. Okay, so what we are going to do is to define H bar lambda of sigma, which is equal to H lambda beta H eta of sigma plus beta times the number of edges in E lambda. Okay, so basically what I'm doing is just here, I'm putting +1, and I'm considering this new Hamiltonian. Okay. And, well, it defines exactly the same, I'm not changing anything in the physics of the system, okay? It defines exactly the same measure because I'm multiplying the weight of every configuration by a constant. And now if I do this, okay, so if I define Z lambda, which is equal to the sum over sigma in omega lambda of exponential h bar lambda sigma, well, this is subadditive. Okay, this is subadditive. Okay, so what I have is that the lambda 1 union lambda 2, it's equal to the sum over. Okay, so I'm just looking separately as I take the sum over all the configuration, but I'm summing separately over the spins that I see in lambda 1 and the spin that I see in lambda 2. Then I get exponential h lambda sigma 1 sigma 2. Okay, so this is equal to, well, this double sum, and then I have exponential h lambda 1 sigma 1 plus h lambda 2 sigma 2 time exponential of sum over x in lambda 1, y in lambda 2, x neighboring y, beta sigma x sigma y plus 1. Okay? No, I'm just writing an equality. I'm not forgetting any terms, okay? I'm just saying the Hamiltonian in the union of the boxes is just the Hamiltonian in each boxes plus, well, the edges that I've forgotten, but now all of them have a positive contribution. So if I want an inequality, I can just ignore this thing. And now I can just factorize this sum, okay? And I get that this is larger than the lambda 1 times the lambda 2. Okay. So I've shown that something is subadditive. The problem is not that it's not the thing I want to take the limit of. So maybe I have to justify that this is okay. That this is not a problem. So okay, what we have, so if I define f beta h, which is equal to log 1 over lambda log z lambda, well, this is equal to f beta h plus, okay, basically plus what we have is that z lambda, just by definition, it's equal to exponential beta e lambda times z lambda. Okay, I've just changed the Hamiltonian by this amount. I get this for every configuration, so I can just factorize it. Okay, so when I take the log, what I get here is beta times the cardinality of e lambda divided by lambda. Okay, and now what I want to say is that if lambda n converge to ZD in the Van Hove sense, then E lambda n over lambda n converges to which value? Anyway, okay, this should converge to a constant if this converges into Van Hove sense. What's the value of the constant? Yes. D.
Is the volume of lambda beta?
Yeah, here it's volume of lambda. Yes. Okay, so the idea is that if you convert in the Van Hove sense, okay, everything's, it's like when you have a square box. So, I mean, basically, most vertices are internal vertices, if you want. They do not touch the boundary. So they are attached to 2D edges. And somehow, I mean, you can just give them half of the edges for each of the edges they touch, because each edge touches 2 vertices. Okay, so maybe this is a good exercise to stop. Okay, so try to prove this. And why is this interesting? Well, this F bar, this is subadditive. Okay, no, this log Z bar, okay, this log Z bar is subadditive, this Z bar is submultiplicative. But if we prove convergence of this, somehow, if we prove convergence of this, we also prove convergence of this, okay, because we know that the difference converge. Okay, so by kind of what we have done, I mean, is we added to f something that converges to a constant, and this gives it nice property, okay, because this makes the interaction between boxes of a given sign. Okay, so I will just stop here, and next time we will start from this observation and use it to prove the theorem. Questions?